It is my great honor and pleasure to host Fred Douglis at exactly the 12th, that means one full year, a month after month of Industry Spotlight podcasts that were organized by Corporate Liaison Program of Santa Clara Valley section of IEEE. We have one of the members, Shmuel Shotan, here. Hello, Shmuel. Fred, I have known for close to 30 years, not quite, but close, maybe 29 years. I don't even need to read his bio. I visited him at many places where he worked. We have similar background of system software, data migration, process migration, all kinds of system software areas. Fred will present his talk titled Fleet Fast Lanes for Expedited Execution at 10 terabits. He, as of a few days, recently his company changed the name to Peraton. It used to be Perspecta Labs to Peraton Labs. And with no further ado, Fred, please go ahead. If I can please ask everyone to turn off your videos and also to mute yourself. If you have questions, please type them in Q&A. I will be asking questions at the very end. Thank you. Fred, please go ahead.
All right. Thanks. So for those who have never heard of Peraton Labs, if you haven't heard of Perspective Labs either, I'm not surprised. When I joined about 3 years ago, it was Vencor Labs, and before that it was a few other things. But some people may be familiar with Telcordia or Belcor, and it used to come from that. So that's what this lab is. By and large, we do government contracting. And so this is a DARPA-funded project, FastNICs, that I'm going to be talking about. I'm co-PI along with Seth Robertson. We're both chief scientists at Peraton Labs. Chief scientist there you can think of as sort of similar to distinguished engineer or something. There we go. Okay, I'm going to start by just thanking and acknowledging our partners on this. These are our subcontractors. We have 2 people we're working with at Columbia and their students. Karen Bergman is doing the photonics work, and Mingo Suk is professor in the EE department doing the electronics for optical networking. And then Alex Aiken is at Stanford over on your side of the country, and he's also at SLAC, and SLAC is working with us on the Stanford Legion project, which is a big part of what we're talking about here. So DARPA FastNICs is a program that started just over a year ago. It was started by Jonathan Smith as the program manager there. And JMS, as he's known, put out this in the BAA, the call for proposals. And the chart on the right is showing the difference in processing capacity and network capabilities versus the way that we can actually get data through a system. So the notion was that at the extreme ends, the processors and the networks could deal with things in the order of 100 terabits aggregate capacity, but the networks just were not keeping up with that. And so he's trying to move this sort of red line of where the networks were up to the FastLink's objective line, which is 10 terabits per second, and just try to see what would happen if we could improve network performance, both in terms of bandwidth and latency, whether we could apply it to a particular domain. So the problem space here is machine learning. We're trying to get a couple of orders of magnitude improvement by using optical interconnects. And our partners on the FastNICs project are USC and Raytheon, the 2 technical area 2 programs that are doing the machine learning algorithms on top of our software and hardware system. So Fleet, I explained before in the title, Fast Lanes for Expedited Execution at 10 terabits. We're trying to do this with a hardware and software approach. Seth is leading the hardware component of this, and I'm leading the software. So for the hardware side, we're trying to use off-the-shelf systems as much as possible, but we use a particular customized component that we'll get into to support the optical transport and to allow us to do dynamic topologies, creating topologies on the fly for the applications that we need. On the software side, we want to leverage open source high performance computing, which is specifically we settle on the Stanford Legion project. And so integrating that with this special support that we have and the dynamic interconnects. So this talk is a blend of a description of sort of the project as it was proposed in late 2019 and started in, as I said, just over a year ago, and how it's behaved over that first year. I mentioned at the end we have a paper that's in the process of appearing in IEEE Internet Computing describing this if you're interested in more details. And so we talk about some of the lessons both on the hardware and software side as we stand so far. But this is obviously very much a work in progress. We're still in the early stages of this program. Okay, so so this is what the proposal was. Our system has many similarities with that and some variations, as I'll be getting into throughout the talk. So the idea is to have PCIe, standard networking, interconnect, extended into the optical domain. So we get the full PCIe bandwidth, and PCIe is something that we're constantly coming out with new generations. We're using PCIe 3 and 4 in the system we have currently. PCIe 5 is just becoming available, and they've already started talking about what PCIe 6 will look like. So this is something that can follow the technology curve very easily. One key innovation for the hardware side is this optical NIC. So we have what we call an ONIC. It has an FPGA to do both the data transfers and onboard computation. So it's basically a smart NIC, as a lot of other systems have referred to this. The photonics for this are being developed by Columbia. The FPGA software is being developed by Paraton. And so this deals with a number of things in terms of one of the special aspects that we have to deal with here is sort of dealing with the dynamic topologies. If a device can come and go, we need the PCIe system to be able to deal with that and to understand how to interconnect with it when it's available. So it also will do streaming processing. So as things are being passed through, we can transform it. And it also will provide an application accelerator that allows applications to take advantage of the FPGA. And we use that to get some of the latency metrics that we need. And then there's a MEMS switch in the center, which allows everything to connect to everything in theory, but it gets programmed at any particular time so that any particular ONIC has a path to some other ONIC elsewhere in the system. So to go into this diagram on the right in a little bit more detail, the upper left with the one circle is showing a couple of clusters. The idea is that we would start with two clusters at 3 terabits per second, connected with optical switches. They would be interconnected, and then they would also connect to the later generation 2 clusters that would be able to interoperate at 12 terabits per second. A cluster would consist of 4 servers. This is the idealized thing. We actually, when we deployed things, there were cost constraints on the DARPA side, and so we negotiated that down a little bit. So our cluster at the moment for one cluster is three of these servers. And then the number of GPUs and NVMe and such is also something that's evolved. The MEMS switch has a special amplifier that deals with getting we have the lasers that feed things into these photonics, as I'm going to talk about in a moment. And the MEMS switch also has non-volatile memory. And we can reprogram this relatively quickly in the order of milliseconds, although to actually then reconnect and talk to something takes somewhat longer. In the upper right, we have centralized resources that are accessed via PCIe. So in this case, we're showing GPUs, but these could be NVMe. The idea is that each GPU would have an ONIC associated with it. And so these aren't tied to any particular host and can be used by any server in the system. And next level, number 4, we have a server with a bunch of CPU blades and ultrapath interconnect. And each one of those blades, shown on the bottom left, has a whole bunch of cores. And each one has 3 PCIe connections. So each one of those can have an ONIC. So that means that we have a total of 24 ONICs in one of these servers. And so that allows it to communicate with many different devices simultaneously. On the other hand, the GPUs, as I'll get to a little bit later, with one ONIC, have two connections, and they can communicate with specifically two different devices before being reconfigured. The ONIC on the right, and I'll go into this in much more detail in the next couple of slides, but it's basically a fast FPGA. It has 3 PCIe interfaces. One goes to the host or the GPU or whatever it is it's connected to, and then 2 of them go out to the optical switch. And the PIC, the photonics integrated circuit, is the thing that makes the, connects it between the optical switch and turns it into the things that get passed through the system. So to go into the photonics architecture a little bit more, in the first generation cluster, we have the MEM switch in the center. We have a whole bunch of these lasers, each one, so on the left for, a bunch of GPUs and NVMe, we might have 10 ONICs, and that means there are 20 fibers going from them into the switch and 20 fibers from the laser. On the right, we have a whole bunch of servers. So at this point, we have 72 fibers, 72 from laser, twice that going to the switch. And so all these can interconnect, and we can basically reprogram the MEM switch to make use of them for in a particular application, however we want to. The ONICs look like this. So this is blowing that up. So the PCIe on the top left interconnects with the optical module. So each one of those, if we go over here, hopefully you can follow the mouse here, goes to the electronics integrated circuit and the photonics integrated circuit. This thing is modulating everything, turning it into the bits that get passed through here. On the FPGA, we also have what we call the TA2 accelerator core. The TA2 is the neural network applications that we talked about, training and such. And so the idea is that they can offload things into that and do both transformations or just use it for applications that the FPGA is well suited to. So DARPA and the BAA specified a number of metrics. So they have the technical area. 1.1 is the hardware, 1.2 is the software, and then 2 is the neural network training. So we're not going to focus on the TA2 areas too much. But for the TA1, the notion was that it should have 2 terabits connectivity at the end of phase 1, which is the first 2 years. So 1 year now from where we are right now. 5 terabits at phase 2, 10 terabits at phase 3. We realized that having 3 generations of system would just be too much, and so we proposed to go from phase 1 to phase 3. And so we're not going to have an intermediate one at 5 terabits. The latency from a link to the core scale from 100 nanoseconds at phase 1 down to 20 nanoseconds at phase 3. And then on the software side, want to be able to get on the order of terabit per second of actual software throughput up to 6 terabits. So in each case, it's on the order of roughly half. And the software round trip time was intended to be was described in the BAA, the call for proposals, as core to core on the order of microseconds down to 100 nanoseconds. We realize as we get to the next slide that the throughput is easy to achieve with this level of aggregation. So with PCIe 3, 1 lane would be just under 8 gigabits per second. Typically PCIe has 16 lanes, that's 126 gigabits per second. But then we add up all the slots, the aggregate throughput is 3 terabits per second. When we go to generation 5 in the next phase, or in phase 3, that takes us up to 12 terabits per second, which is even more than the 10 required in the BAA. And for that, we would move from Cascade Lake to Sapphire Rapids is the plan. So we consider the throughput problem not to be a big issue. We thought there might be some other issues here in terms of integrating with PCIe, but that's not a problem. The latency, on the other hand, we described as hopeless. We basically realized that when you factored in all the latency within the different parts of the system, that we were not going to meet the particular numbers. If I go back a slide and you look at the round trip times and latency up there, that just doing it sort of like CPU to CPU would not work. But instead we said, okay, well, the latency sensitive application code can run in the FPGA. So if you go into the FPGA and back out and you don't have to take some of these other steps, then we'd be able to achieve that. So how do we try to get the TA2 teams to meet their goals? We have the notion of a planner, which is going to figure out the resource allocation and the dynamic network topology changes. So optimize all the problems away. That's the idea. The idea is that under the covers, we wanted to sort of be smart enough to get the data at the right place at the right time. So that's something which is a combination of what Legion does in terms of optimizing the transport and what this planner has to do. We want to change the topology, so break applications up into execution phases. And then we can say that, okay, in a particular topology, maybe we need a ring in one case and a tree in another, or hyperplane or something else. We thought when in doing this proposal that that basically having fast CPUs, lots of memory and lots of bandwidth would be the best way to approach this. And by the way, we would also have some NVMe and storage and GPUs. In practice, we realized as soon as we started talking to the TA2 teams that for their applications, GPUs were far more important than any of the rest of this. And that furthermore, as I'll talk about a little bit later, GPU connectivity was extremely important. So let me talk a little bit about reconfigurable networking. So the idea is that in our original design and in the design of the ONICs that are being produced by Columbia, the NICs have two optical interfaces. That means any given NIC can talk to both the host and something else. In this case, C1 is talking to B1 and to D1. And so that means that any two hosts can exchange at the full bandwidth. And they can also be passing it to other hosts while they're doing it at the full bandwidth. So the NIC at A1 could receive something from D1, pass it to B1 and to host A simultaneously. And we can use external resources like NVMe disks or GPUs or what have you that are disaggregated. They don't belong to a particular host. You don't have to send something into the host and have that host go and pass it out or and copy it elsewhere. So all of these things, wherever they are, they appear like local PCIe resources. And so a much more complicated example of a pipeline might be something here. We have a bunch of data in the bottom left. So NVMe disks D1 and D2 are being passed around to these GPUs. So they flow through, they go straight from the NVMe to the GPU without passing through any host. The GPU can be passing something else simultaneously to another host, and they can flow through the system. Each of the NICs here could be doing streaming processing where the FPGA is operating on things as is being passed through the system. So all these things would be aggregated. And in this example, you could have 80 terabits per second in flight when you consider all the different points that are simultaneously passing things through the system. So some of the lessons and experiences that we've had on the hardware side at this point. I mentioned before GPU connectivity. We viewed the aggregate GPU connectivity as meeting the goals of the program. That if we had a CPU that could load into a whole set of GPUs at a total of 3 terabits per second, then that was a success. It turns out that it was much more important to our application users to be able to pick any particular pair of GPUs and have them communicate with each other at much higher speeds. And so the way that we're addressing that at this point is our second cluster, instead of being a clone of the first one with, which is with just the Supermicro servers and the external GPUs, is we have a set of Lambda Labs A100s that we've just acquired. And these have an NV switch that can connect any set of GPUs to each other with high bandwidth. And so we're using this as the test bed for the first phase of the project. And we're going to see how things look going forward in terms of what the next level will be. What we really would like to do is to do some sort of combination of ONIC and NVLink bridging. So we could send something from an ONIC into the NVLink, and then, for example, share it with multiple GPUs, or have multiple ONICs that could send in parallel, and all of them get the highest bandwidth into a particular GPU. And so and also using the ONICs, we would be able to connect GPUs that aren't in the same NV switch environment so that they would be able to get the high bandwidth. So that's sort of the direction we're going in. We would like to be able to try to interoperate with NVLink, but it is a proprietary protocol, so there's some issues there. For the ONIC custom hardware, we had a problem in terms of our timeline, partly because of COVID. Things shut down for a while, both at Columbia and with some of the other partners that we're working with. And so our original goal to have something within a few months from now was pushed out. And actually, I'm sorry, original goal, I think it was earlier than that. Anyway, so what we did was we are working on the ONICs that they currently are in the process of producing. We expect to have them in several months. But in the meantime, we've been using something similar to the ONICs, but using completely off-the-shelf components. And so instead of the specialized Columbia photonics, we're using off-the-shelf transceivers, but we're using our own FPGA to interoperate with them. And so what happens is we now have comparable performance as long as we're using 2 fibers instead of 1 for each connection. And it's also somewhat higher latency. But this does give us the interesting aspect that we have now 4 different network connections instead of 2 from any given ONIC. And so that means that we have much more flexibility in terms of the topologies that we can create. And also, it's a lot less limiting. If anything that uses an ONIC needs to talk to multiple parties, it can do so, but just at somewhat lower bandwidth. Another issue, and this actually leads into the next point, which is switched versus circuit connections. So our assumption originally was that if we picked any particular ONIC, that if it connected to 2 destinations, yes, we might reconfigure it at some point later on, but it would be enough for it to get sort of enough data, and there would be enough locality that would be communicating with a particular set of destinations before it had to be reconfigured. The catch is that as we've started thinking about it, it looks like with these disaggregated GPUs and NVMe devices, they might simultaneously need to communicate with more than 2 parties. So if any given device actually needs to communicate with 3 or 4 parties using that original architecture with the 2 communicating the 2 fibers, you would be limited. You have to keep switching off. So one solution to this is to combine what we call freeways, the circuit switched freeways that have the established connections and no particular extra overhead. And have, for example, 1 fiber out of the ONIC communicating directly with 1 party at the best bandwidth and the lowest latency. And then we would also have a second path that would go into a CPU someplace that would have lots of connections that could forward it as needed to whichever party it needed to go to. So that would essentially be packet switching. And then the alternative for that, as I said a moment ago, is that if we have more than the fibers, we can leverage that ability and at the cost of the lower bandwidth. What else we want to do is to figure out the best way to plan for this. So if we have if a particular application that wants to make use of this, we want to figure out, okay, what's the way to get the minimum number of changes, have the minimum number of cases where we have to have lower bandwidth if we're using multiple destinations, and when is the right time to reconfigure the topology in order to change a phase so that something can go from one connection to another. So now I'll move into the software part of the talk. So on the software side, as you've seen, we have a hardware environment with lots of possible uses and lots of configurations. We have many different CPUs, but many blades within this, all sorts of different interconnects, all sorts of different peripherals that will function independently of the host. And we saw different ways that we can configure that topology, but we have to figure out how that should be done at the software level. So how do we decide which things to connect, what should be connected before the execution, when are the appropriate times to change it during execution? So one aspect of this is that we decided on the Legion programming environment. So I mentioned before, Professor Aiken at Stanford has been leading this project for several years. It has a wide customer base, if you will, at this point, and is using a lot of national labs in particular. A couple of quotes from Legion I think will help for those who are not familiar with it. It's a data-centric programming model for writing high-performance applications. And the idea is that because it understands the data and how it's used, it can implicitly extract parallelism and the data movement operations in a way that allows the programmer not to have to worry about some of those specifics. So the idea is to automate and hide those operations under the covers. So we decided this would be a good fit for the kind of applications we were doing. The challenges for this primarily are integrating the hardware with the lower level runtime. We've done much of that at this point, and modifying Legion to make use of this, both in terms of how it uses that lower runtime and the higher level applications that I'll be talking about in a moment. So this is a modified diagram, the system architecture of Legion with a few things plugged in. So the things on the upper left are what we thought we would do when we first started with the program. There's a high level language called Regent that compiles down to C++ and is specially geared toward Legion and the kinds of applications it uses. And so we thought that people would come in here and use applications on Regent. As it turns out, there's something else called FlexFlow, which is specifically geared toward deep learning and has a framework, has support for PyTorch and Keras TensorFlow. So it turns out that basically everybody that we're working with on this program at this point is looking at FlexFlow, and Regent has gone by the wayside. And we'll talk a little bit more about that in a moment. The fleet planner is this magical thing I talked about earlier to figure out how to best use the resources system-wide. So we've tried to figure out how to allocate things onto specific nodes and decide what the network topology should be like. The mapper is something that's already part of Legion, which handles per node resource management. So there's a notion of a default mapper, which is something that can be run if there's nothing that understands the system better. But if people have a particular use for either the hardware that they're on or the particular application that they're running, they can write a custom mapper, which does something a little bit more customized for the application and the environment. Either way, they code to a particular mapper interface that's below that, which leads into the Legion runtime. Legion I've already talked about. This is kind of the glue that makes everything happen. Realm is the lower level of Legion. So it's the runtime that deals with things like networking, GPU access, and FPGAs are being added to it. This is something that we're currently working on. And also we've added the fleet module under there. So GasNet on the bottom left is the thing that Legion normally uses. So that's the common way for most systems to interoperate. And it itself is done at Lawrence Berkeley Labs. It has a number of different components that can talk to many different types of networks underneath. So the idea is that it provides a machine independent view to Legion, and all the machine dependencies are held underneath. We originally thought that we would plug something into GasNet, but in the end we decided that it would be better to plug it into Realm directly, both for simplicity and to eliminate one layer in the software stack, given that we were worrying so much about latency and such. So this is how Fleet supports the distributed training of DNN. So FlexFlow from Stanford and Slack looks at different ways to go and allocate applications and how things should be run. And in particular, to define this thing called the sample operator attribute and parameter, or SOAP, search space. So SOAP has lots of different terms. It's not web services SOAP. It's something else. The operator space is basically how to parallelize the operators, like convolution, matrix, multiply, and such. Sample and parameter are how things are distributed across devices. And then for attributes, it's things like if you have images, you might distribute things based on attributes of the data. So the application developers are already using PyTorch and TensorFlow. So running this on top of FlexFlow works very well. And so the question is, how should we integrate it into our environment? So Legion now runs a customized direct memory access that specifically uses the FPGAs and everything that we have. So we've modified Legion to deal with Fleet, and we're modifying that Legion to now work with FlexFlow. FlexFlow has this notion of a simulator. It basically looks at the resource consumption and runs things for a little while to figure out how long things are likely to run, and then uses that to predict how it should allocate things for resources. And our planner would be using this and then also be looking at how that factors into the network topology, given that we can change how things are connected on the fly and before things run. And the other thing is that at least for one of the teams that we're working with, they might like to actually plug in their own planners. So they could have, we would have an interface in the end that allows them to specify, okay, we think we can figure out a better way to decide how to allocate resources. And so they would be able to do that and then push something down to say how things should run rather than our planner doing that. So some of the lessons that we've had on the software side. So one of them is simulation fidelity. So FlexFlow does this profiling I mentioned, and it uses a combination of actual runtime for the operators to say how long things take to execute, but more of a static model for what the network looks like in terms of latency and bandwidth. And it turns out that in more diverse environments, that's a lot harder to predict. So with inaccuracies in terms of the communication performance, you would wind up with poor solutions. So if we look at the right side, we see what Shi Luo at Slack on our team there modify the simulator to get a better network model. And on the right, we see with two nodes on the right-hand side in particular, the blue is the old simulated time, the orange is the simulated time with its modifications, and the green is the actual time. So the simulator tends to underestimate the total execution time, but the modification with the more accurate network model does a far better job of matching it. We look on the left side, that's the same is pretty much true for AlexNet at the top for the deep learning resource model, I think it's DLRM anyway, from Facebook. That is the simulated time actually was a pretty good fit for the old simulator and overestimates it now. So that's something that we need to look into. So we think that these changes are going to make things more accurate. But we have opportunities to extend this model further if we have to. The next software lesson is about over-optimization of the network layer. One thing that both Legion and GasNet have assumed is that when you build a system, you know what you're running underneath it, and you configure that when you compile it, and because of that, you can do optimizations that allow you to get better performance, and that's certainly true. The catch is that it means that you can't mix and match different networks very easily. So in particular, we thought that maybe GasNet, because it's meant to deal with heterogeneous networks, would be well suited to allowing us to use, let's say, Fleet on the one hand and InfiniBand or something else on the other, and to have an application that could somehow talk to both. That's not the case, and only you basically have to pre-configure one or the other. So we think that this is more of an engineering problem, not sort of fatal flaw, but we have to decide how to go from here. We had originally looked at adding Fleet to GasNet, as I mentioned. We decided instead to build it directly in, and so now we have to revisit this and decide, okay, if we want heterogeneity, there are two options. One is to add Fleet to GasNet and bite that extra complexity and somewhat higher overhead, and modify GasNet to allow for multiple networks. We hope that's doable, but we understand from them that they believe it to be a challenge. And then the other possibility is to try to modify Legion to deal with both GasNet and Fleet at the same time. And that's probably an easier path, but it's also, I'm sure, going to be a challenge, and we have to decide how necessary that is. So for the planner, we really want to deal with how the planner can scale up to something with much higher large networks and high dimensional parameter spaces. And it's a problem because we want to deal with both the things that FlexFlow currently does, which is basically placing the operators and the data for the deep neural networks, and simultaneously dealing with how to configure the switch. What should the network look like? So the way we're approaching this is that we take the FlexFlow simulator and start with that and come up with something which is a reasonable placement program based on its own techniques and using some sort of static configuration of what the network looks like. We can use the GPUs and the FPGAs in the system to try to improve on that simulation. So that's another thing that we need to optimize. We use these offline profiles of what the hardware looks like using the hardware profiling, and we iterate over this with a static topology. We can look at what the operators might look like, and given the static operator placement, we can figure out how we can change the topology. Well, where we really want to go is to something that factors all these together. And so if we optimize both the algorithms and how we interpret the hardware, we can try to do something that we'll start with the static topology, as we said, but we want to finally get to a point where we can change the switch configuration dynamically and figure out how the ability to change the switch environment would allow us to place the DNNs differently. So I want to thank DARPA for sponsoring this, and Jonathan Smith in particular. All of our collaborators at USC and Raytheon, and our subcontractors at Columbia and Slack. There are a few people who are involved with the Legion program, but who are not actually on the project and not being paid for by this, but have been extremely helpful in everything we've done. Mike Bauer, Jihao Jia, Elliot Slaughter, Sean Treichler, and Wei Wu. I want to call out Jihao and Sean in particular for all the help they've given us on Slack and responding to all of our questions about this. There's a large team at Paraton Labs that I will not bother to read out. And I mentioned at the beginning of the talk that there's a paper on Fleet that's appearing in Internet Computing. Preprint is available if you go to the Internet Computing website or look in the Computer Science Digital Library or IEEE Explorer, you can find it. And with that, I can take questions. And that email address will change in a couple of weeks.
Thank you very much, Fred. Excellent presentation. I really enjoyed it, every single slide. With this, I would ask audience to type in the questions in the Q&A. We already have one question, and I have a bunch of questions as well. You can also, if you have problems with typing, you can ask in person. So let me start with, I think, a little bit of trick question. A feature of GPU that I find most attractive is the triangulation, much like the human eye may do in image processing. Any projection specific to this feature on the results presented? That's Dr. TV Gopal.
I don't have any particular insight into that. You know, I'm not on the application side, and so you know, I think that would be something to take up with the teams that are doing the DNNs, or if there's a question about, you know, one interesting point here, I think, is that while the project has been geared toward DNN training, there are a lot of other ways in which the same hardware environment could be put to good use. You know, you can imagine doing all sorts of other GPU applications on it, but I don't have any particular expertise in GPUs myself.
Okay.
So I will punt on that.
No problem. So let me ask you the question about latency. I understand you are in the very beginning of the project in many ways, but do you have any sense where you are with respect to latency?
I think it's a little bit early to put out numbers. We've done some preliminary numbers, measurements, but it's very much still being tuned. So I can't really say.
Okay.
Sorry.
Okay, no problem. So then the next question is in terms of reconfigurability, which is, I think, one of the nice features that you're offering and really forward-looking. How much is it contributing to your overall benefits?
I think it's a big part of it. I mean, we expect that it's not if you have an application that's running in something at this scale, that there's going to be a certain dynamism to it, that it's not always going to be the case that the same parties communicate, you know, a lot over the entire lifetime of it, but instead there are phases where certain parties interoperate. And so, for example, you can imagine something being brought in by, to one node that's operating on something. It does a bunch of work, but then at some point it's passing things on to a different one. So we think that the ability to reconfigure it, certainly for different phases, that basically, I'm not sure, we don't yet know whether we will find it really essential and really effective to be dynamically changing something on the fly, that at this particular moment we are going to reconnect this port to that port and change who something is talking to. We've built it into the design. We think that it may prove useful, but it's hard to say. I think that the idea of phases, where you make a plan at the beginning, you say you're going to run for some period of time, you're going to do this, and then you're going to sort of pause for a moment, change a bunch of network connections and reconnect things so that they can connect to other parties much, very efficiently, and then continue with the next phase of the application. We anticipate that that is a big win. But again, it's too early. We don't have the actual applications doing that yet, so we can't prove that yet.
Okay, I have another question by Debduchit. In one of the performance numbers, you had presented the software throughput and software latency. Can you please elucidate on how it was calculated?
Well, those were the targets that were given by Jonathan Smith, and we're likely to relax those targets because he basically, when he originally designed the program, he put out a call with an eye toward a design that he thought would satisfy his goals. So he mentioned, even I think in the BAA, the notion of basically connecting directly into memory. So the idea is that instead of having these things connecting into something which feeds the processor or the GPU or whatever it is, that you would have some sort of direct access to memory over the optical link. And that was his view of what he was expecting. And he did some back of the envelope calculations that that suggested that those were good targets. In the end, we decided that was not a feasible approach. We actually went to our teammates at Columbia when we first started talking about working with them, and they described some work they had done a couple of years earlier that was very much along these lines, and may have been what suggested to Jonathan Smith that was a good approach. But it turns out that they said that the particular hardware that they were using for that was no longer available. It was basically no longer an option going forward. And so we took this particular approach instead. That's not to say that it won't be an option, in future years using some other technology. But we had to bypass it for this. So getting back to the original question, I think the reason for those particular numbers was that it came from sort of a back of the envelope notion of what might be possible. In the end, for our proposal, we basically said, well, we might achieve these going in and out of the FPGA, but that was kind of hand wavy, and everybody, we and they recognized that it was an attempt to try to address the number, but because we saw that it just wasn't feasible in terms of like core to core.
Okay. So my next question is, but I got another question just come in. In your architecture or applications, what is the main limitation, if any, with the FPGA? Is it the latency only? That's from Jay.
I don't know yet. I mean, that's still under development. I think that the latency is one aspect there, and that is something as we pass it through. If we talk about trying to meet those latency numbers going into the rest of the system, it's going to add some overhead there. But in terms of other limitations, I think part of it is it's not my bailiwick, and so I don't have a particular sense of what else to discuss there. But if you drop me an email, I might be able to get you a better answer.
Okay, so the question for me is more on the business model. There's a lot of smart NICs work around the community. I guess FastNICs is at the extreme. But in terms of business opportunities, what are your thoughts? Where could it fit?
Yeah, we are very interested in technology transfer for this, and I think that there are certainly opportunities far beyond this program. So the DNN training was the sample application that was meant to drive this and to demonstrate its feasibility. But I think that could be used for all sorts of other things. And I think that in essence, what we were trying to design here was sort of a mini supercomputer, if you will, of a bunch of off-the-shelf components, but where the special connectivity, the high bandwidth, low latency, and flexible connectivity would allow it to be used in ways that people have not done here before this. So for that, I think it can be used for any sort of application, anything that needs large scale distribution with interconnects, with high performance interconnects, and especially for anything where the distribution is something more flexible. If it's something where you have a static environment, people have been building supercomputers for decades, right? And they have particular layouts and they come up with a particular topology and say, this is the way you use this system, right? And what we're saying is, here's a bunch of nodes, here's a bunch of other resources, mix and match, put them together like Legos. And so we think there will be a lot of other opportunities there, and we're certainly interested in talking to people who might want to use it. But we don't have any specific examples of that yet.
Okay, we have a next question from Gerald McGuire. Would UPI be a better interconnect than PCIe?
That's a good question. We focused on PCIe in part because it was a way to use a lot of these things off the shelf. So there are all these different devices that already will handle PCIe. UPI might, give us better performance, but the question is, how would it interoperate with all the other things that we're trying to interoperate with? So could you build something from scratch that would do that? I imagine so. But we were trying to do something that met a particular budget as well. And so we were going for as much off the shelf as we could.
Okay, I have another question for you. You were mentioning what Jonathan Smith was expecting, and that is access to memory directly rather than through PCIe. What is your take in general on fabric attached memory, be it disaggregated or not?
Well, that's a loaded question coming from you, Dan. No, I think it's a great idea, and I think it's what he thought was going to happen. We did not pursue it here, and I guess that he did not have another proposal from someone else that he found compelling and something to pursue. So it's not clear that it couldn't have been done, but it's so I think that it certainly allows a lot of opportunities for new sorts of applications, and I think that we'll certainly see more of it. And
I apologize, I did not mean to ask a loaded question. I was rather asking you for your position. I mean, fabric attached memory has been proposed for quite a few years now, but it still hasn't taken on, probably because of the slower speed of non-volatile memory or many other reasons. So I was just curious, what is your take? What is the time frame when it will finally be coming? It appears that it's inevitable, but inevitable.
Well, I think that you folks in HP are far better positioned to answer that question than I am.
Okay.
So, anyway, I'll leave it at that.
Okay. I think I exhausted many of my questions, and we have a bunch of questions from others. Do we have any other questions from audience? Shmuel, I know this is your area and you're hesitant to ask, but you are welcome to ask in person. You don't have to type it.
You're muted if you are asking.
Yeah, I'm putting Shmuel on spot.
I know, but he's muted.
You're muted, Shmuel. You need to unmute.
Yeah, there you go. I figured that there's an action after the declaration. So I'll follow up with an email, because the question that was asked about FPGA was something dear to my heart, and I struggled with it and found solution on various projects in the last 10 years. So since it's not your bailiwick,
Yeah, I'm more on the
you.
software
I'll
side.
follow up
It's-
to the email
That would
if
be
you
great.
can introduce you.
I'd be happy to
That's
introduce you to the folks who are more
appreciate
involved in
it.
that and be in a better position to answer your questions.
And Shmuel, you're welcome to talk to me about FPGAs as well. I do quite a bit there.
Ooh, perfect.
Okay, so with this, I'd like to thank Fred. Extremely interesting talk, really extremely interested. This is our full year. Every month we have presented a talk to you, to our audience. Some of you, I think, attended every single talk. If you have any suggestions for the future talks, we have lined up a few talks, but we always have opportunities. Please approach Shmuel, myself, Paolo, Mary Baker, Zoran, and others who are leading this corporate liaison program for Santa Clara Valley section. We are delighted to serve you, and we are looking forward to organizing more talks. Okay, with this, thank you very much, everyone, and hope to see you next month as well. Bye. And thanks, Fred, again.
Thanks, Brett.